Hey there, Math 126 fans. Somebody's asking me about this. Why do we square the distance when we're trying to minimize? That's something I sometimes say I don't like about what textbooks do, but let me explain here. The explanation I usually give, I'm going to go into more detail, and I'll do a 2D and a 3D problem. But I often tell students, if I asked you which is bigger, the square root of 17 or the square root of 14, I bet you could tell me without pulling out your calculator. So think for a second, which one of those do you think is bigger? And most students tell me right away, square root of 17 is bigger. How do you know that? So if you have the square root of blah, and you have the square root of stuff, think for a second what it means if this is smaller than this. What else has to also be true? If that's true, well, this has to be true. Technically, that's what we mean by an increasing function. So if you have two numbers, if x1, I feel bad, this sounds too mathematical. But if you have one number that's smaller than another number, and you plug it into a function, and the output is smaller, we say the function is increasing, if that's always true. Whenever you have an increasing function, it will be smallest when the inside is smallest. It will be biggest when the inside is biggest. So it's not really anything special about square roots. It's the fact that it's an increasing function. But that's kind of a silly thing, because another way to say it would be if I have y equals the square root of blah, and I take the derivative, so let's say there's a square root in there, or the square root of a function. Maybe I'll be a little more mathematical, and then I'll explain these problems completely. Well, what is the derivative of a square root? So it's not essential that you use this trick. It really only saves you like a tiny fraction of a piece of paper. So I sometimes go, why do I have to always answer this question? Because it's not even necessary to do the problem. So the derivative is this times the derivative of the inside. And if you think about that, means the derivative is 1 over 2 times the square root of, so it's basically that original function times f prime of x. And since we're setting that equal to 0 in these problems, this doesn't matter. So this little trick about squaring both sides, you can think of it in terms of an increasing function. You can think of it in terms of the derivative rules. But ultimately, none of that matters, because you're going to end up just getting 1 is f prime equal to 0, no matter how you think about it. Okay, let's actually see the problem, because there's other questions students have about this. So before I do the 3D problem, I thought I would do the 2D problem and try to answer several of the common questions. So here's a 2D version that doesn't really require calculus. A problem that says, assume you're allowed to walk anywhere along this line, y equals x, but you cannot leave the line. So find the point. So find, and I'm making up this question, xy on the line y equals x that is closest to 4, 0. Now that question can be done in lots of different ways. In fact, I hope you're thinking, I could find the perpendicular line. That's lovely. That wouldn't require calculus at all. But let's do the calculus approach, because it'll help us in the next piece. So what we say is we're trying to minimize the distance from a point to another point. We can write that out. We're trying to minimize this distance. Now, one confusion students have is this function I'm about to write is not the equation of the line. It's the equation of the distance. And that's not linear. Anyways, plus y minus 0 squared. But I often say we haven't put the constraint in yet, because if you're allowed to stand anywhere you want, you would stand right here and you'd be as close as possible. What's preventing me? The prevention is that the y has to be equal to the x. So we put that in there. We put an x right there. And that gives us a one variable function for the distance. So the distance given as a one variable function of x is x minus 4 squared plus x squared. So the question the student was asking me was, why in the textbook do they immediately square and analyze this instead? So the quick answer is that the minimum of this will occur at the same x value as the minimum of this. When the thing under the radical is smallest, the overall thing is also smallest. They have the same minimum x value. But let me show you some visuals to try to answer a few questions relating to this. So I prepared this. I'll shrink it up a little bit here. So there's this picture. I made it so that I can move this point around. So there you go, you can see it. I labeled the distance, so you can see the distance is about 3.4, 3.3, 3.2, 3.1, 2.9, 2.8, 2.9. Okay, so somewhere in here is the minimum when they're perpendicular. So what we did is we constructed the formula for distance. The formula for distance is a new formula. It looks like this. It's that purple formula. I graphed it on the same set of axes, which is sort of weird to do. But the minimum distance is that low point. That's including the square root. If I get rid of the square root, it's a different function. Totally different function up here. But you'll notice that both of them have the minimum at the same place. So the one on top there is without the square root, is the g of x. And the one on the bottom is the f of x from our little description. So anyways, I don't know if that helps. So that's what we're studying as the distance. The minimum distance occurs right lined up with that low point. And in this case, it's 2. How do you find the low point of one of these functions? Well, you can use either one. So let's finish with a little bit of calculus. I'll move my picture over. Get out of here. And let's do this. So if I use the direct function, you get f prime of x. And what I like to do is write 1 over 2 times the square root of the mess. Because the mess being all of this stuff underneath, times the derivative of the inside, which is 2x minus 4 plus 2x. And then I'm going to set that equal to 0. The reason I didn't write that whole thing out is because I can multiply both sides and then I end up just needing to solve this when this is equal to 0. So I can divide both. I better not do too much simplifying. Let's expand it out. And you're going to get 4x is 8. And you're going to get x is 2. And that was that point. That was that point for that function. You know, f of x when it was lowest. The reason they don't line up at all is because that's the distance. That's what the length of this is, the height of that. It's a new function we constructed. Could we have just taken the derivative of this? Sure. It's not the same function, but the minimum occurs at the same value of x. Plus 2x, you set it equal to 0, you get x equals 2. Now g of x is somewhere way up here. And it's not really interesting to us, but the value when it's minimum is the same. That's what's going on. So it's a lot of fuss for something we don't even need. So again, you don't need to do this. It's not essential for the problem. That's the part I don't like about it, is students spend so much time thinking about this thing that really has nothing to do with the problem. It just has to do with the fact that the square root's an increasing function. But that is not essential to this problem. What's essential is we set up the distance and we find the derivative. We find when it's equal to 0. Okay, so the cool thing is you could do that really for anything. You could just change the function to something else instead of y equals x. Yeah, it might make this more complicated, but calculus does a good job of finding minimum distance. Okay, so let's go to the actual problem. Sorry, no one's listening at this point. If you're still listening, give me a like or a comment. I hope this was of value. But this is something that I've been asked about many times over the years. Same thinking. We're trying to minimize the distance from a point to a cone. It's actually a double cone. That's why there's 2 answers. The cone goes down as well. And it's going to happen at the same value, the same plus or minus. What's the closest point? Well, what are we trying to minimize? We're trying to minimize distance. So let's play the exact same game. This is what the student was asking, which I really appreciate you asking this question. So the minimum distance is, the distance is the square root of x minus 6, y minus 2, and z squared. But again, without a constraint, you would just stand on there. If someone says you have to stand on the cone, then you're going to replace. And in this case, it's pretty nice because it's already written in this form. So in this case, I can get a 2-variable function for my distance, which is this: x minus 6 squared plus y minus 2 squared plus x squared plus y squared. And I'm trying to minimize this. So what the textbook does is they do this unnecessary step where they drop the square root, and that confuses everybody. Again, that is not essential to the problem. I have no issues with the student doing that. My issue is that for years I'm explaining this thing, which really has nothing to do with the actual problem. Just a little side trick. I don't like side tricks. They're nice if you can see them. I said I'm not against it. I just know that it's been a distraction. Okay, so we want to minimize this. So what I would do if I didn't want to use the trick is I would say, okay, I need the derivative with respect to x and the derivative with respect to y. It's going to be 1 over 2 times the square root of the mess. This is also going to be 1 over 2 times the square root of the mess, which I don't care about, times the derivative of the inside, which is 2x minus 6 plus 2x, and I'm going to find when that's 0, and 2y minus 2 plus 2y, and I'm going to find out when that's 0. And if you do the partials of g, you're going to get the same thing. So let me show you the visuals for that. Here we go. So here's this 3D. That little purple point is the point 620. Here's the surface. Here's the distance to it. I made it so that I can play around with these, and you can kind of see there is a minimum somewhere in there, but this one you can change the y's too. So where in the world is that minimum? Well, it's somewhere in there if we're just trying to eyeball it. Not there, because I think it would look perpendicular. Maybe somewhere in here. I don't know, I'll tweak the y as well. Maybe we're close, I don't know. How do we find that? So we constructed this new function, which is the distance. That's this red thing. And it turns out that the low point on the distance corresponds to when you are closest. So if I could get this thing to line up, I know from the student's answer that this is 3 and this is 1. That lines up directly with this point here. So maybe I'll label this point 3, 1, negative square root of 10. Let's do positive square root of 10 at the top. Let's make it also purple. So there's that point at the top, but that corresponds if you went straight up to the bottom point of the distance. So I'm doing this to add this extra layer because students often go, what? It doesn't make sense. The cone doesn't have a minimum. We're not trying to find the minimum of the cone. We're trying to find the minimum of the distance. That's that thing. If you get rid of the square root, you get a whole new function that's like way up here. I gotta zoom way out to see it. That blue function. But the low point is at the same x and y value, which is the same as the point when you're closest. Okay, that's overkill, but I hope that answers your question. Let me know if it does.